And now we go to the third talk about the persistency of linear programming relaxations for the stable set problem by Elisabeth Rodríguez-Heck, Karl Stickler, and Matthias Walter, and Stefan Weldge. And Elisabeth is giving the talk. Where are you, Elisabeth? There you are. No, you have to unmute yourself, and I was told I can't unmute you.
Yeah, okay, now
Good.
You can hear me. Now I will share my screen. Okay, so I hope now you can hear me and also see my slides.
Yes, yeah. Everything is fine.
Okay, you don't see this green rectangle or?
Yeah, we do.
I do see even that rectangle, but it doesn't bother too much.
Yeah, well, let me just try to share, otherwise the desktop. Otherwise I will just, okay, that should be better, right?
Right.
Yeah,
now,
okay.
Yeah, good, very good.
Okay, thank you. So thanks for the introduction. What I will present is joint work with Karl Stickler, Matthias Walter, and Stefan Weldge. And here we will also be talking about the stable set problem. So even though it was mentioned in the previous talk, let me briefly introduce it again. So we are given an undirected graph G and a vector of weights for the nodes W. Then the weighted stable set problem aims at finding a stable set S in G, maximizing total weight. And a set S is stable if G contains no edge with both endpoints in S. Now, it is well known that this problem is NP-hard, and as was also mentioned in the previous talk, we can model this problem as an integer programming problem, for example, using this model here, where we introduce a variable xv, a binary variable for every node. So we are in the node space. This variable takes value 1 if and only if node v is selected to be part of the stable set. We maximize total weight, and with these inequalities, we enforce that for every edge of the graph, we cannot select both endpoints to be in S. So the set of feasible solutions of the LP relaxation of this model is often called the edge relaxation, and we will denote it by R edge of G. So a common approach to solve the stable set problem is to maximize the objective function over the edge relaxation, which can be done efficiently because it's a linear program, and to use optimal fractional solutions to gain insights about optimal 0-1 solutions. This happens, for example, when we apply an algorithm of the branch and bound type. Now, this is all probably very well known to all of you. Something that is maybe less well known, but which was briefly mentioned in the previous talk, is that for every graph G, the polytope, the edge relaxation on G has a property which is called the persistency property. So this is a result by Nemhauser and Trotter from 75. So what is this persistency property? So a polytope P has the persistency property if for every objective vector C and every C maximal point X in the polytope, so this point will have some integer, some fractional components. So for every such C maximal point X, there exists a C maximal integer point Y in the polytope, such that on the subset of components of X which take integer values, this C maximal integer point Y takes the same integer values. So this is a vector with perhaps some integer, some fractional components. For those integer components, we know that there exists a maximizing integral solution for which these values will be the same. So the implications are that if X star is an optimal, perhaps fractional solution over the edge relaxation with a subset of nodes corresponding to variables taking value 1 and a subset of nodes V0 corresponding to variables taking value 0, then there exists an optimal stable set S star containing every node in V1 and not containing any node in V0. This means that the variables corresponding to nodes in V0 union V1 can be deleted, so we can potentially reduce the dimension of our problem. But of course, this only has practical implications if the sets of those integer components, V0 and V1, are large enough. Now, it is known that for the maximum cardinality stable set problem on random graphs, the probability of obtaining a single integer component is very low. But persistencies have proven useful for structured instances, so for graphs which are not random, with other objective function than the cardinality function, so then the one which assigns weight 1 to every node. So in particular, persistency for the stable set problem implies persistency for unconstrained quadratic binary programming. And in this context, the persistency has been used by the computer vision community to solve or to reduce the dimension of very, very large image restoration problems. And there is also a polynomial time algorithm to compute the largest possible set of these variables here that we can potentially eliminate for unconstrained quadratic binary programming. Now, on the other hand, we also know that we can model the stable set problem in different ways, which will be associated with polyhedra, which will be different. So we denote by P-conv of G the convexal of characteristic vectors of stable sets of G. So this is also called the stable set polytope. This would be the perfect formulation, but as it was mentioned in the previous talk, we don't know a description for this polytope for every graph. Now we will consider other formulations. So we will regard an LP formulation for the stable set problem as a map R that assigns to every finite and directed simple graph G a polytope RG, such that this polytope RG contains the same integer points as the stable set polytope, so that it contains the characteristic vectors of stable sets. Now, it is well known that the edge relaxation provides bad LP relaxation bounds in general, which motivated the study of other formulations. And many of these came by studying families of inequalities used to strengthen the bounds of this edge relaxation. Some examples are clique inequalities, odd cycle inequalities, and so on. So now we know these two things, that the edge relaxation provides bad LP relaxation bounds, but that it has this property which is sometimes interesting, which is the persistency property. So it is only natural to ask whether there exist other linear programming formulations for the stable set problem, which also have the persistency property for every graph G. So this is the main question that motivated our research. And in our paper, we provide a negative answer for this question for formulations satisfying certain mild conditions. So more precisely, this is our main theorem. We consider a formulation R satisfying some mild conditions that I will detail in a minute. Then R of G, this polytope, has the persistency property for every graph, if and only if R is equivalent to the edge formulation, or if R is equivalent to the formulation giving the convexal for every graph. So this equivalence here means nothing else than that R of G, the polytope, will be equal to the edge relaxation of G for every graph, and similarly here. Okay, so what are our mild conditions? I will briefly mention the first two. I will spend some more time on the third one. So the first two say that for every graph G, every facet defining inequality for the relaxation R of G with support U is derived from facets of the perfect formulation on the subgraph induced by U, and each such facet defining inequality for R of G is valid for induced subgraphs. Here I will talk more about this third condition, which says that for every pair of graphs G1 and G2, and for nodes V1 in G1 and V2 in G2, we have that R, our formulation, applied to this special graph here, is equal to a special sum of the two formulations on the two graphs separately. So what is this operation here? We call it the one sum on V1 and V2. We apply it once to graphs, once to polytopes. So when we apply this one sum operation to graphs, we say that the one sum of G1 and G2 at nodes V1 and V2 is the disjoint union of the two graphs, but where we identify V1 and V2. And when we apply this operation one sum to the corresponding polytopes, we define it as the convexal of points xy in the Cartesian product of R of G1 times R of G2, where we identify the variables corresponding to V1 and V2. So when we apply the one sum to graphs, we identify nodes. When we apply it to polytopes, we identify, so to say, the corresponding variables. Here we have an example. So if this is our graph G1, our graph G2, nodes V1 and V2, this would be the one sum of these graphs. And this condition says that when we apply our formulation R to this graph here, so it is given by, it is defined as the formulation R of G1 and the formulation R of G2, where we identify these two variables. So if you're looking at the paper, you will see that there is an extra condition, but I don't mention it here because we recently understood that that extra condition was not necessary. Okay, so which are some well-known formulations satisfying our conditions? For example, the clique relaxation, the odd cycle relaxation, or the intersection of both satisfy our conditions. So they fall under the cases considered by our theorem, which means that they do not have the persistency property for all graphs. Do you have any questions until here? Okay, so then I will continue with a proof idea. So half of the paper is a proof of this theorem. So I want to give an idea of how we prove this result. So here I've only repeated our theorem. Now the if part is easy because if R is equivalent to the H formulation, then it has the persistency property for all graphs. This was the result of Nemhauser and Trotter, which motivated our research. And if our formulation R gives the perfect formulation, so the stable set polytope for every graph, then it has the persistency property by definition. So the only difficulty comes in proving the only if part. So what we will prove is that if our formulation R is not equivalent to the H formulation or to the convexal, then there exists a graph for which R of G does not have the persistency property. So just to restate the only if part a little bit more clearly maybe, if R is not equivalent to the H formulation or to the convexal, this means that there exist graphs G1 and G2 such that the polytope R of G1 is not equal to the H relaxation on G1, and such that the polytope R of G2 is not equal to the stable set polytope on G2. So we prove that if this holds, then there exists a graph G star for which R of G star does not have the persistency property. So in a sense, we only have to construct a counterexample, right? Because we only have to find this graph G star and prove that the polytope does not have the persistency property. So what we will do is that we will provide a graph G star and an objective function C star together with a node, disproving persistency. So we will show that for this function, every C star maximal solution over R of G star gives the value 0 to this particular node, and that every C star maximal solution over the stable set polytope for G star gives value 1 to this particular node. So in the version of the persistency property that we stated, we actually don't even have to prove that this is the case for every C star maximal solution, but only that there exists one. But we prove this. This gives a stronger property, which is sometimes called strong persistency. Okay, so what is the challenge then if we only have to provide a counterexample? So the main difficulty comes from the fact that R, this formulation can be anything. So for example, R can be defined by all facets, defining the convexal except one facet or two facets. So we don't know how these facets look like. We don't know which facet we are leaving out. We are working with all graphs together. So R is quite unknown. This is where the challenge comes from, but fortunately R satisfies our mild conditions. Okay, so this is what we will do next. We will construct this graph G star to begin with. So to construct this graph G star, we base ourselves on the following lemma, which says that there exists a graph G, a vector of coefficients of weights C and a node V, such that when we maximize C over the polytope R of G, we obtain a unique maximizer taking value at least 1/2 on this particular node. And these graph vector and node are such that when we maximize C over the stable set polytope on G, we have a maximizer assigning value 0 to this particular node. So I will not give all the details of the proof of this lemma. We can discuss it later if you want, but I will show you why it is plausible that we have these things. So remember that by hypothesis of the only if part, our formulation R is not equivalent to the convexal, which means that there exists a graph, this graph G, for which these two polytopes are not equal. This means that we will have at least one optimization direction given by C, for which we obtain different optimal solutions. So they will differ in at least one coordinate. So this is a general idea. What I want to show you is how we use this lemma. I will show this on an example where we consider the formulation defined by the edge inequalities and the odd cycle inequalities for cycles of length at least 5. We define G star as follows. We consider a graph that we call G in such that the polytope R of G in is not equal to the edge relaxation on G in. So such a graph exists because the other hypothesis of the only if part was that R is not equivalent to the edge formulation. So for this example here, we can consider the odd cycle of length 5. In this case, R of G in will contain all the edge inequalities and the odd cycle inequality of length 5. Here we only have the edge inequalities, so the polytopes are different. Then we will use our lemma to consider another graph that we call G out, that we will copy around G in, and we will paste it at every node of G in except for one node. In this case, for example, node 1. This pasting will be given by the one sum operation. And in this case, for this formulation, this triangle is such a graph G out because we have the vector giving weights all ones to every node, such that when we maximize it over the relaxation here, which is in this case the edge relaxation, we will have a unique maximizer, which will give value 1/2 to every node. This one, the node that we will paste will be node V out. And when we maximize the cardinality stable set problem over, so when we consider the integer problem here, we will have two maximizers giving a value 0 to this node here. So the one selecting either this node or this node. So this graph G out comes out of this lemma. So we apply this one sum operation, and this will be our gadget graph G star. We still have to define an objective function C star such that we contradict persistency. So we define it as follows. For the triangles, for the graphs G out, we will take in this case the same vector of the lemma, so weights all 1 for the triangles. We only have, it only remains to define a weight for this node here, node 1. So we will assign it a weight of value epsilon, strictly positive, but small enough so that when we optimize over the relaxation, it is not worth to give this node any value other than 0. So when we maximize this function C star over the stable set polytope for this graph, for each triangle, we can select at most one of the vertices to be part of the stable set. And if we select the vertices so that these two vertices here, 2 and 5, take value 0. This means that by selecting node 1, so by setting x1 equals 1, we can still gather this small value of epsilon. So every C star maximal solution over the stable set polytope will give value 1 to this node here. Now, what happens when we maximize C star over the relaxation? So this is a little bit more difficult. So the nodes 2, 3, 4, and 5 will take value at least 1/2. In this case, they will take value exactly 1/2, because remember that before applying the one sum, this graph G out was given by this lemma, and maximizing cardinality gave us a unique maximizer assigning value 1/2 to every node. Now, in this case, if epsilon is small enough, when we apply the one sum, the only thing that we will be doing for these nodes here is that we are identifying them. So we are adding constraints, so to say. So we can only get a value which is equal or worse if we forgot about this node 1. And it will be in our best interest to keep this optimal solution, which was optimal over this graph, separately, giving value 1/2 to each of these nodes, if epsilon is small enough so that it's not interesting to give here a different value. What we still have to see is that assigning value 1/2 to each of these nodes implies that this node 1 here will take value 0 when we optimize over the relaxation. And this is easy to see in this case because remember that we have the odd cycle inequalities. In particular, we have the odd cycle inequality for this cycle here. So this missing facet that we didn't consider until now, it will imply that when we assign value 1/2 to each of these nodes, this will completely saturate this new facet. So node 1 will take value 0. So this is easy to see for this example, but it also can be generalized thanks to a proposition by Sewell, which says that if we consider any facet defining inequality for the stable set polytope, which is neither a bound or an edge inequality, then we have a certain relation between the coefficients of this inequality, which implies that giving a value at least 1/2 to every node except for one of the nodes will completely saturate this new facet. So this is a key component of our proof.
You have 5 more minutes.
Okay, thank you. So with some effort, we constructed a counterexample. So this graph and an objective function for which, when we consider the integer problem, we will always select this node. But on the relaxation, we will always set the corresponding variable to 0. So this is what contradicts persistency. But here I chose to show you a fairly easy, nice example. There are some hidden difficulties in the proof. So here in particular, what was easy is that when we were taking the optimal solutions of this triangle separately, and we put them together in the cycle, the remaining solution was still feasible. So this is not always the case. Other difficulties are that the definition of the objective function is not straightforward. So among others, we have to define this value epsilon small enough so that it's not worth to give a value different than 0 to node 1 when we optimize over the relaxation, but we don't know this relaxation, so this takes some effort. We have this potential problem of the non-feasibility when we apply the one sum to the graphs G out and the graph G in. And so in general, we don't have much information on R. So another place where this poses problems is that when we show that every C star optimal solution over R of G star does not give any positive value to variable 1, we make a proof by contradiction. So we assume that it's not the case. We try to construct a better solution, but this solution has to satisfy all unknown facets of R. So here is an example which illustrates more or less some of these difficulties. Here we also consider triangle inequalities, graph G in, the graphs G out, and the optimal solution over of the relaxation over the graphs G out separately assigns value 2/3 to these nodes, and this will not be feasible when we apply the one sum. So just to give you a very brief idea of how we deal with this. So we define a function G, which considers the contributions of the graphs G out, forgetting about node 1 for a moment in the objective function. So we study the function modeling these contributions in terms of the right-hand side of one of those missing facets. We see that the function has some nice properties. It's strictly increasing up to the value of the right-hand side. And in particular, with the Sewell property, we see that x1 will not contribute to the maximum. So for small epsilon enough, we can construct another solution, which is a bit different than the one given by the G-out graphs, but which will still set node 1 to 0 on the relaxation. So here are some other hidden difficulties. I also wanted to have some nice handwritten slide, although here I scanned the structure of the proof. I only talked in this presentation about some parts, so about this part here, about the construction. If you're interested in more, I'm happy to answer any questions, and I thank you for your attention.
Thank you very much for this nice talk on the interesting persistency property. That can spare time of research, of trying other formulations. And please, Michele is asking a question, and so I give him the word.
Yeah.
Michele.
Hello. Thank you for the talk, first of all, and for the result to all the authors. Is it conceivable that if you have a formulation that does not have the persistency property and defines a polytope P, any formulation that is stronger in the sense that it defines P prime contained in P cannot have the persistency property?
So you mean in general for other problems?
Yeah, in general. Forget about stable sets.
Okay.
I mean, I'm not asking to tell me yes or no.
Yeah.
You know if this is very far-fetched?
So I wouldn't see immediately how to generalize our proof because we heavily rely, among other things, on this Sewell result, which talks about facets for the stable set polytope. So that's one of the components where our particular construction wouldn't work.
Do you know any other major examples? I asked it to Michele too, of the persistency property.
So yeah, so the one actually where we got our attention to this property came from quadratic binary programming unconstrained. And then we understood that in fact, the property for those problems comes from the stable set property. So that's this paper by Hammer, Hansen, and Simeone. And so, so here.
Okay.
So yeah, so that's the other big problem about which I know about this persistency property. But one interesting open question, for example, is whether the persistency generalizes from quadratic to higher degree unconstrained programming, and that we don't know.
And in these cases, the persistency property is used also in algorithms, right?
Yes. Yes. So that's why what caught our attention, because so before I was studying reformulations of polynomial binary problems into quadratic problems without constraints, so problems of this type, and the whole motivation came from these problems in computer vision, where they use the persistency property for the quadratic unconstrained problems to solve very, very large problems. So I think up to millions of variables with other, so they perhaps don't solve them to optimality, but they reduce the dimension very much.
So for stable sets, it's mainly in practice that it is used, or is there some identified class of graphs for which maximum weight stable sets are solved by using a lot the persistency property, or maybe only the persistency property, or mainly?
Yeah. So the one I know is precisely this one, the quadratic binary and constraint case, because the property for this case, for this quadratic case, is derived as a special, by writing these problems as a special case of weighted stable set problem.
Okay, thank you very much. I don't see hands raised at this time, and we were very busy. We didn't upload each talk, so let's at the end of this session upload all the 3 talks. So, and we have time, so please 3 times as much uploads as usual.
Okay, thank you. Thank you all.